Start the recording. Okay. Sharing my screen. Top notch. First of all, happy Halloween tomorrow. I know, not today, but tomorrow. I did add these notes. It's a hypothesis test, and I said try on your own for Thursday, and here we are on Thursday. And I did add these because otherwise we'll slip too far behind. And so, but what I want to do is just talk about the solutions that I posted, right? So that we've at least heard the solutions, right? And then I copied and pasted them into today's notes as well, so they'll be there. So you'll have them in duplicate since we'll talk about them today. We were talking about the GSS, the General Social Survey, which found that 571 out of 670, so roughly 85% of Americans answered the question on experimental design correctly. And then, do these data provide convincing evidence that more than 80% of Americans have good intuition about experimental design? And so from here, right, we have a one sample proportion, which is 0.85. So we'll just use the rounded value of 0.85. And we want to know if this 0.85, so 85% or 0.85, is significantly more than 0.8. Okay? Now that's how we're going to figure out what our P naught is, right? Our P naught is the value that I want to compare my sample proportion to. And so I want to compare 0.85 to 0.8. It is more than 0.8, but I want to know if it's significantly more than 0.8. So I've got step 0, check the conditions or the assumptions if you have to assume some stuff. First off, we have the independence condition, which is usually satisfied by just having a random sample. So it doesn't say, but we assume that the sample was randomly selected. And so that's what I mean by checking your assumptions. It's really just stating things that you're assuming before you can proceed. The optional n less than 10% condition, right? N of 670 should be less than 10% of all Americans, which I feel comfortable saying it is. In this particular question, right, we were asking, do these data provide convincing evidence? As soon as you need evidence, then you're doing a hypothesis test. If it said construct a 90% confidence interval, then you would be doing a confidence interval. Right? Now, I only checked the normality condition for a hypothesis test, whereas if the question was asking you to do both, then you would have to check both, right? Or if you're only doing a confidence interval, then you only need to check it for the confidence interval. What's the difference between the two? For a hypothesis test, we need at least 10 expected successes. Okay? And the expectation comes from your P naught, right? What are you expecting it to be if P naught is true, right? If P equals P naught is true. Okay? And so we have N times P naught, which gives us our expected successes. Okay? So if P is 0.8, I would expect 536 successes, which is more than 10, which is great. So that's satisfied. And we need at least 10 expected failures. Right? Same thing. N times Q naught is 134, which is more than 10. So then what we can say is that the conditions are satisfied. And we can actually go through and answer the question. If it was a confidence interval, what would be the difference? Then you would need at least 10 observed successes and at least 10 observed failures. Right? But I know that I observed 571 successes out of 670, so it's relatively easy to figure out how many observed successes and failures I have. But that's for a confidence interval. Now, what I tried to do is not make any notes around it, right? We spent a lot of time kind of making notes around the hypotheses and around the test statistic. And so this is kind of bare bones minimum what you would need to do in order to answer the question. Okay? And so step one, you don't have to list the steps. I do just because it emphasizes that we're always following the same steps, right? But it might be helpful to list the steps if you find that they kind of guide you. But if not, as long as you state your hypotheses, right? Your null hypothesis is that P must be 0.8, right? I have to assume that it is 0.8 until I have proof that it's greater than 0.8. So my alternative hypothesis is that P is greater than 0.8 because I want to know if it's more than 80%. And so that's where the greater than came from. It's more than 80%. What we saw last day is that if I'm only concerned about one extreme, we call this a one-sided test, right? Which we kind of parking lot for a little bit, that knowledge, until in step 3 when I need to figure out, hey, which tail am I interested in? Okay? I like to make a note that it's a one-sided test. You don't have to, but it's a nice thing because then you can look at it later. Step 2, you want to do the test, right? And so in this case, doing the test means to calculate Z. Yeah? And so how your formula sheet is set up, if you go there, and I have spares if you don't have yours, or if you don't have one, I guess, or it's on Moodle. If you're doing a hypothesis test, I give you the general form of step 1, and I give you the general form of step 2. Okay? And so here, step 2, calculate the test statistic. It says I have to calculate this Z. Oops, not there, here. Which I did, right? How far is 0.85 from 0.8 with this standard error? And I found that it was 3.236 standard errors above P equals 0.8. Good. Now we use that to find the p-value, right? The p-value is the area in the tail, right? It's the probability of seeing something as extreme or more extreme, assuming the null hypothesis is true. So then we said, and I kind of drew it out. This part is optional. I just wanted to have it there so you can see it. But I took our Z that we calculated, 3.236, and I drew it here. Okay. From the table, the T table, if you try to take 3.236 and you try to place it along this line, you would find that it's between 3.091 and 3.291. So it would fit in somewhere in here. We want a one-sided P because we have a one-sided test, right? So earlier we said we'd parking lot that one-sided, right? And now we're bringing that back, right? So we don't need it until step 3, but we do need it. So what the table tells us is that at 3.091, the area in the tail is 0.001, right? And I've got spare tables if you don't have one. And the area in the tail for 3.291 is 0.0005, very, very small, right? So even though it feels kind of like cheating in a way. All we can really say about the area in the tail for 3.236 is that it's somewhere between 0.0005 and 0.001. That's okay. Right? That's as far as the table will take us. And what you'll find in the assignment is that it asks you to find the actual p-value using software. So you can use Excel, or a lot of calculators do the Z calculation if you want to try that out. Huh? Since on the test you'll be using the t-table, I want you to be comfortable with writing it out properly. So how we write it is we say, using the t-table, we find, and notice that I've put the absolute value of the z that we calculated, right, just in the middle. Okay. And so really I'm just kind of using shorthand for what we did up here, right? I'm saying, hey, using the t-table, I find that my z is somewhere between 3.091 and 3.291. So my one-sided p-value is somewhere between 0.0005 and 0.001. It's easier to articulate that if you've managed to kind of sketch it out like this. Notice that because I tend to only use the less than sign, right? You have to list them from smallest to largest, which is kind of the traditional way of listing inequalities anyways, right? Go from smallest to largest. Otherwise, you want to be careful with which way you face your inequality. This way, you just don't have to think about it, as long as you remember to go from smallest to largest. So our p-value, our one-sided p-value, is going to be very small, right? Somewhere in this range. I don't need to know anything more in order to draw my conclusion, which is my step 4. Remember, the conclusion has 3 separate parts. Usually the conclusion is 3 marks out of a total of 7 usually. And so this probably won't make sense to you now, but the stating your hypotheses is worth 2 marks. Because everything that you do following how you set up your hypotheses has to follow what you said the hypotheses were. So even if you had completely misunderstood the question, then that would be reflected here. But as long as you were able to follow through, then, which is kind of difficult if you've got it wrong, but as long as you show that you follow through, then that's okay. So there's a lot of weight on the hypotheses. Doing the test, although it's a lot of math, it's not what we're here for, right? I don't care. Can you use your calculator? Sure, that's nice, but this is just 1 mark. Because as long as you follow through with whatever you found, I'm happy. And so that's what people find confusing about this course, right? But I did all the math. I know, but we do a little bit of math. But the important part is the interpretation and the conclusion, right? Kind of the understanding of the problem. Similarly, 1 mark for the p-value, right? Did you use whatever z you told me that you found properly? Did you find a p-value properly? So not a lot hinging on those 2 values. Conclusion is 3 marks. Because I don't have enough room on either side to write it out here. Where are those 3 marks coming from? The 3 parts of a conclusion, right? And so the first part of a conclusion is you have to compare your p-value to the alpha level, right? And you have to write it out. So since our one-sided p-value is between, and this is just writing out in words what you found earlier, right? So as long as you're following through with what you told me in the p-value section, even if it's completely wrong, if you follow through in your conclusion, I'm happy. Okay. So it's between 0.0005 and 0.001. It's less than our assumed alpha level of 0.05. That's how you compare the p-value to the alpha level. You have to say what it is, right? Tell me everything that you know. Say what you're comparing it to, right? Is it less than or is it not less than 0.05 or whatever alpha level I tell you to use? Okay. The second part of the conclusion is your conclusion in terms of H naught. Remember, we do all our testing assuming the null hypothesis is true, right? And so, which means we have enough evidence to reject H naught in favor of HA, right? And then the one everyone loves to forget, what does that mean in terms of the question? Right? You've done all this work and you want to get through it all, but really what you have to do is you have to reword the question as an answer. So that's not hard. It's just tedious and something that you have to remember, right? But it's the reason you're taking this course, and so it's good for 1 mark. Therefore, these data provide convincing evidence that more than 80% of Americans have good intuition about experimental design. What I want to point out here is on the test, if for some reason things aren't working, right, and you can't find your Z or you forget how to find your p-value, okay, then just make something up. Say, I don't remember how to find the p-value, so I'm going to use this number. Now the hitch is that it has to be a reasonable number, right? Maybe say that I'm going to assume that the p-value is somewhere between 0.005 and 0.01, something like that. Maybe it's between 0.02 and 0.025, right? But using the table, you can just pick something that you like. Seems reasonable, okay? You don't get marks for that because that's wrong and made up. But you can still get marks for your conclusion. Okay? It's not something that I want you to do, but I do, if you're ever feeling stuck, then I want you to do that, right? Kind of a last resort, right? If you're struggling and knowing now that, okay, my Z calculation isn't worth very much, my p-value isn't worth very much, right? My conclusion is worth a lot, right? Make something up. Say, I'm going to assume the p-value is somewhere between these two values, and then use that, right? And I know what you're thinking. Well, couldn't I just memorize a standard conclusion and just always do that for part marks? Yes, you could. I'd still be kind of happy because the conclusion is the moneymaker. Huh? So, there, a full hypothesis testing question, right? Kind of start to finish. I will not get you to check the assumptions by hand, right? It'll be a multiple choice question, right? And so they're not really worth memorizing. It's more for assignment questions and things like that. practice questions, right? But on the test, step 0 is exactly that. It's just a little multiple choice question. And then you do step 1 through 4. Oh. Nice. This was also in the slides from last day that I added after class, just kind of quickly, but it says 11% of 1,001 Americans responding to a 2006 Gallup survey stated that they have objections to celebrating Halloween on religious grounds. Hey, it's kind of apropos. No wonder I kept it. It's Halloween tomorrow. In case you missed it. At a 95% confidence level, the margin of error for this survey is plus or minus 3%. So we have to remember what the margin of error is. But that's that whole plus minus chunk in your confidence interval, right? A news piece on this study's findings states more than 10% of all Americans have objections on religious grounds to celebrating Halloween. At a 95% confidence level, is this news piece's statement justified? Now, we've seen this before, right, where we use a confidence interval to basically test a hypothesis, right? And so what's the hypothesis? If I add that in here, your null hypothesis would be that P is 10% or 0.1. Your alternative here would be that P is greater than 0.1. They're claiming it's greater than 0.1 or more than 10%. But when we build our interval, so from 11%, which is the point estimate, we move down 3 to 0.08, and then we move up 3 or 0.03 to 0.14. And so here we have our 95% confidence interval. And what we notice is that the 0.1 or 10% is in this interval, right? Which means I don't have enough evidence to reject H naught, right? Which means I can't conclude that it's more than 10%. And so what we can say is no, since 10% is within the confidence interval, right? In fact, we are 95% confident that between 8 and 14%, right, and 10 is in there, of all Americans, blah, blah, blah. Little recap, because it was in there. We have our, yeah, sorry.
Sorry, that question really confused me. Wouldn't that be correct? This 10% is in.
Oh, but it's not more than. So it would only be correct if 0.1 was here and the entire interval was above.
Oh.
Does that make sense? Nice. I'll remove that because that could be confusing, but yeah. Good. 11 is higher than 10, but the entire interval captures 10. So then 10, we can't say more than 10. We can say 10, but the problem is we can't say more than 10. Inference for one proportion wrapped up. We've got a population parameter P, we've got our point estimate P hat, our conditions were independence, we have the random sample and the 10% condition, right, which we've done some practice checking, and we need at least 10 successes and failures, right? Notice how it doesn't specify the expected or the observed, right? And so, let's see here. For a confidence interval, we need the observed. And for the hypothesis testing, we need the expected. If it's not satisfied, then we apply randomization, but it'll always be satisfied for us. What I want you to try to see on the formula sheet has kind of some hints on how to check the conditions, right? And so what we said is for a confidence interval, right, the standard error, which in general is p times 1 minus p, or q over n, for a confidence interval, we use p hat, right? And how did we find the observed? Right, so for a confidence interval, the observed successes were n times p hat. Yeah. So on your formula sheet, right, if we go there, I'm gonna mark it up so it's at the top. In the square root, you have the standard error, and in the square root, we're using p hat and q hat, which tells me that they're the ones I'm going to use to check my conditions, right? And they're going to be the observed successes and failures. Whereas if I'm doing a hypothesis test, notice in my square root, I use my p naught, right? And so that's kind of my reminder for how I check the conditions. All right. And so we want for a hypothesis test, we use the expected successes and failures. And so for a hypothesis test, the expected successes, and I'm assuming if you can do the successes, you can also find the failures. Right. There's a lot of that in this course. As long as you remember how to do one, you can do the other one as well. So in the hypothesis test, the standard error uses p naught, which is also how we check the expected successes. Nice. So far, we've only seen one type of question, right? And so I'm going to start introducing a new type of question every day now. And so this type of question that we're about to introduce, I call it two sample proportions. And so it's our first new type. We spent a lot of time with one sample proportion, developing some rules, and we'll see some variations on those rules. But in general, right, we're just going to keep doing a confidence interval, do a hypothesis test for each of these types of questions. We're graduating to two proportions. So now I have two sample proportions, which means I want to, we want to compare the two proportions. Now with two samples, we introduce kind of more layers, right? If I have two samples, then sample one is going to have some sample size, right? Which we denote by an n subscript 1. It might have some number of successes, x subscript 1. And it might have some p1 hat, which, if you have to calculate it, is x1 over n1. The the pickle is, so does sample 2. Sample 2 can have its own sample size and it can be different. And so sample 2 is going to have a sample size n2. It'll have some number of successes, x2, and it'll have some sample proportion p2 hat, which is x2 over n2. So we introduce a lot more variables because we have now the same number of variables, but for 2 separate groups. And so here I'll say note n1 does not equal n2 necessarily. They are allowed to equal each other. They're allowed to be the same, but they're allowed to be different as well. Maybe I should bring this over here. But they are allowed to be the same. So our goal is to compare these 2 proportions, right? P1 and P2. Now, usually how we compare things is by subtracting them. If they're the same, they should subtract to 0, right? Whereas if they're different, they'll be something other than 0. And so we want to compare the 2 proportions, which we will do by subtracting, which is why it's called the difference of 2 proportions, right? And so it'll look like P1 minus P2. P1 minus P2 is equal to 0 if they are the same. Versus P1 minus P2 will not be 0 if they are different. Page here. So we haven't had this problem before, but on the test, what you'll have to do is you'll have to read all the problems and figure out what type of question do I have, right? And so before, right, we just had one sample and we said 571 out of 680 said this, right? And so that's just one sample, and so we have information from one sample. Now for 2 proportions, right, then I'm going to have 2 different groups, but the same kind of information for each group. And so on your formula sheet, it's kind of a big day, graduation day in a way, where we flip to the back side of the formula sheet and we start chipping away at all these different types of questions. And so today we're working on 2 sample proportions. So I'm gonna drag or grab this whole thing, I guess. Beep. And before we do anything else, I want to take some time and kind of demystify this thing. Because it looks overwhelming. If you look at just this section even, it looks like a lot. But let's start with this guy here. P1 hat minus P2 hat, that's my best guess at what P1 minus P2 looks like. Okay. So it makes sense that I need to know what the distribution of this thing is. Okay. And so this is the central limit theorem for the difference in proportions. That's just theory, and we are using it, but not really, right? And so this is the central limit theorem, which is theory, which we can ignore. It's technically true, but if you want to just kind of scratch it out, it's totally fine. We are relying on it, but we're not going to spend any time developing it like we did for the first one. Okay, that's nice. So you can basically kind of cross that out. Notice that it's big only because you've got information from sample 1 and information from sample 2. Right? Group 1, group 2. Okay, what's next? How about a confidence interval? I want to build a confidence interval for the difference in the proportions now, right? That's how I summarize this behavior between the two groups, right? P1 minus P2. So I have my point estimate, which is my best guess at this difference, which is P1 hat minus P2 hat. We have a Z star, which behaves exactly like our Z star from before. And so that's nice. We know how that behaves. And this is our standard error. I do want to make some notes here. Z star is the same as before. So you use the T table, use that Z star line, and it's the critical value. This square root mess is the standard error of P1 hat minus P2 hat. So it's the standard error of this point estimate. We just use it as is, right? But this is the standard error. Now, when I boil this down, I've got a P1 hat and a P2 hat. P1 hat, Q1 hat is 1 minus P1 hat, right? We've seen that notation many times now. And divided by N1. Then, separately, make sure you don't kind of run these into each other. Find them separately. P2 hat times Q2 hat over N2. And then don't forget to take the square root. But there's really not more information here. It's just kind of big because there's a lot of components, right? Okay. So with our sample sizes and our P1 hat for each group, we could build a confidence interval, and we will. Okay? But that's nice because it looks really terrible. But now that we've broken it down, it's not so bad. If we want to learn about P1 minus P2, which we do if we're comparing two groups, then we might want to do a hypothesis test for this thing. Notice that you've just got two options for your null hypothesis. It depends on how you prefer to think about it. I tend to like the first one, right? Because for me, it's easier to think about comparing these two groups as, hey, if I'm going to assume that they're the same, which is where I have to start, right? Then it's easier for me to think about P1 is equal to P2. And then my alternative hypothesis is going to be about what I suspect is happening, right? Maybe they're not equal to each other, right? Maybe one's greater than the other. Okay. Or this is the same. If P1 is equal to P2, then that's the same as saying P1 minus P2 is equal to 0, right? So you get to choose, pick whichever one you prefer. Okay? So here, pick the one you like. All right, pick the one that makes more sense to you. In terms of your hypothesis test, this will still be step one of your hypothesis test, right? State your hypotheses, but now you have to talk about how P1 compares to P2. And in step two, we're still calculating a test statistic, and what's really nice is that this test statistic is still a Z. So once I have a Z, I know how Z behaves, and I know how to find p-values associated with Z, right? It's just how we get that Z is a little bit more complicated. Now, I prefer the first one. So if you'd like, you can just scratch out the last one. It's a little bit, it doesn't matter. It's on there for a reason, and I'll point out the reason, but I tend to use the first version. I'll show you why. P1 hat minus P2 hat, that's my point estimate. Right? Technically, what we're doing for our Z is we're seeing how far is my point estimate from my hypothesized value, right? Assuming the null hypothesis is true. Now, my hypothesized value, and this is why this version is on here, is that P1 minus P2 is equal to 0. So assuming that's true, technically, you would have P1 hat minus P2 hat. How far is it from 0? Usually, if we're subtracting 0, we don't really make a note of it, right? We just dissolve it, and so that's what we've done here, right? It's not even on the formula sheet. Technically, it's on there, right? But it comes from this null hypothesis that P1 minus P2 is equal to 0, and we're assuming that that's true until we have proof otherwise. What about the standard error? Now, the standard error for the hypothesis test is slightly different. Notice that there are no subscripts on this p hat. Right? We know P1 hat, we know P2 hat, so you have to be really careful, right? But there's also a little note here where p hat is the pooled proportion estimate. And then there's a bunch of different ways that you could calculate it. But really what it is, and I'll go a little bit into the theory, not too much. If P1 and P2 are the same, I should be able to pool them. And so throw them all into one pool and find the combined number of successes divided by the combined number of cases. And that's going to replace my P naught. And so it's just a way of incorporating the fact that, hey, I'm assuming these two are the same. If that's true, then I can find this pooled proportion P hat by combining the successes over the total number of cases. Now, there's a couple of different ways that you could do that. I think the easiest way is this way, right? But that's assuming that you have the successes of group 1 and you have the number of successes in group 2, as well as the sample sizes, right? If you don't, then you would have to do a little bit of work, right, to solve for the number of successes in group 1 and the number of successes in group 2. And so that's why all this mess is on here, just so that you can find that pooled proportion, right? And you don't have to memorize it. That's nice. Q hat, of course, is 1 minus p hat. So once you have your pooled proportion, you can find your Q hat. And then times 1 over n1 plus 1 over n2. What's the difference if I erase my scratch out? All I've done in the second equation is multiplied through by the p hat q hat. So I get p hat q hat over n1 plus p hat q hat over n2. So it just depends on how you like to think about these equations. And one of the reasons to use this version instead of the first one is because it matches the central limit theorem, right? P1 Q1 over N1. Now I'm replacing it with P hat Q hat, right? But you don't need to worry about that background noise. So if you want to simplify things, just use the first one, okay? Because that's the one I'll be using. Well, nice. See, it's not so bad. Pick apart that formula sheet. What do you mean, Emily, that's not so bad? Well, not so bad. Could be worse. Not as bad as it felt when you first looked at it. Pretty good. Okay, let's see an example here. What I'll do, because just to get a little bit fewer pages here, we're going to be talking about survey results where the question was that, or I guess, yeah, the survey question, scientists predict that global warming may have big effects on the polar regions within the next 100 years. One of the possible effects is that the northern ice cap may completely melt. Would this bother you a great deal, some, a little, or not at all if it actually happened? And you don't have to answer it, but I guess for myself, it would bother me a great deal. Right? And so you had to pick one, and I'm gonna delete this here. They did the same survey with in the general social survey, right? I think it's general social survey. Might be societal, anyways, whatever. The GSS, a big survey, asks the same question. Below are the distributions of responses from the 2010 GSS, as well as from a group of introductory stats students at Duke University. Now, what I did before was I just moved the GSS results to be on the right-hand side, only to match the order that they use in the rest of the question, and so it'll make it a little bit easier. But notice that I just copied it over, right? Because we're going to have a group 1 or a sample 1, oops, and a sample 2. We can get a lot of information out of this, and we're used to reading tables like this, right? Contingency tables. And I could ask you, I know, throwback. What if I asked you, hey, what's the probability that someone would be bothered a great deal given that they're a Duke student? Huh? You know how to find that. We're not going to do that now, but we can answer lots and lots of questions with this information, right? So today what we're doing is we want to compare sample 1 with sample 2. Specifically, I have a feeling we're going to focus on this response here, right? Who would be bothered a great deal? And so this is what we'll consider a success. Making all the other categories a failure. So you can just zip those up into a failure category if you want, or what we'll do is we'll just focus on the successes. When we have group names like this, Duke and GSS, or the GSS will summarize as the US or all Americans because it's a general social survey, and so it represents all Americans. So we'll kind of shortcut it as all Americans versus the Duke students, specifically the Duke statistics students, right? Kind of very specific. But we want to compare these two groups. Just like we saw before, we're going to have a parameter. The parameter, remember, is the population that we're interested in. So the parameter is the difference, right? That's the subtraction of the two, the difference between the proportions of all Duke students and all Americans, right? And so that's from the GSS, even though it's not terribly clear now, but now we've established that. Okay, so the GSS represents all Americans who would be bothered a great deal by the northern ice cap completely melting. And so how we can summarize that parameter is P Duke minus P US, or PD and PU or something like that. The important part is we must use question-specific subscripts for the two groups, because just saying P1 and P2 doesn't tell me which group is which, right? And so you want to be really specific. And so we must use question-specific subscripts for the groups. So on your formula sheet, yes, it has 1 and 2, but especially in terms of your hypotheses, if you're saying one's less than the other, then you have to be specific about which one is less than the other, right? So you want to be specific about the groups. Your point estimate, your best guess at what this thing might look like, P Duke minus P US, is of course P hat Duke minus P hat US, which is why we collected samples. And this is the difference that we're actually going to work with. So it's the difference between the proportions of sampled Duke students and the sampled Americans who would be bothered a great deal by the northern ice cap melting, completely melting, I guess. So we've got our point estimate. Bless you. As we saw on our formula sheet, things changed a little bit, but not a whole lot, right? We just need to take into account information from the two groups. And so for a confidence interval, it's still going to be a point estimate plus or minus, or plus and minus, I guess, some margin of error, right? And so from your formula sheet, you know how to calculate that margin of error, right? And for a hypothesis test, we still use Z, which is the point estimate, minus the null value, divided by the standard error of the point estimate to find the p-value. Right? So everything boils down to being the same, even though it doesn't feel like it. Okay? So we just need the appropriate standard error of the point estimate, which is the only new concept, and it's not even new because I just showed you on the formula sheet the difference between the two. But in general, it's going to be P1 Q1, right? I use Q instead of 1 minus P. P1 Q1 over N1 plus P2 Q2 over N2, right? And then square rooted. And then we saw, okay, for a confidence interval, just like the one sample proportion scenario, we use the p hats, right? P1 hat, P2 hat, that's nice. And then for the standard error for hypothesis test, we need to find that pooled proportion, p hat, q hat, but then we get to use it again, p hat, q hat. Let's start with the confidence interval. So the conditions for a confidence interval for a difference in proportions. Remember, we have two groups now, right? Which means I have to basically check the conditions for each group. So we still have the independence condition, independence within the groups. Okay, so within each of these two groups, we have to be able to assume independence. The US group is sampled randomly because it's done through the GSS, and we're assuming that the Duke group represents a random sample as well, right? Even though we couldn't poke holes in it, right? It was from a statistics class. Does that represent Duke students? Well, what are we saying? We're assuming that it represents a random sample, right? Otherwise, we can't really continue. Whether that's true or not doesn't matter. They use kind of sloppy notation here, and so the n less than 10% condition, if you're checking it, would have to apply to both groups, right? So n Duke, which is 105. Maybe I'll make that a little bit bigger. I just had it on there as a reminder. 105 is presumably less than 10% of all Duke students, right? And 680, which is the sample size of the US, is less than 10% of all Americans. So that means that we can assume that the attitudes of Duke students in the sample are independent of each other, and attitudes of US residents in the sample are independent of each other as well. And so that's because we're checking within the groups. When I have two groups, I also have to make sure that I can assume independence between the groups. And usually that's just an assumption that we have to state. And so the sample Duke students and the US residents are independent of each other. Right? No reason to think that someone was sampled for both groups. Right? So they're completely independent of each other. For the success failure condition, I need still the same conditions, right? So remember, the conditions are the same. It's just now I need to check them for both groups. And for a confidence interval, this is specifically for a confidence interval, I need at least 10 observed successes and 10 observed failures in the two groups, right? So you have to do both groups. We have the information, right? And so we have 69 observed successes for Duke, and we have 454 observed successes for the US. And we've also zipped those other categories up into not a great deal, right? Just the complement. And so these will be our failures. I have 36 failures and 226 failures in the US group. I'm going to put this maybe up here. And I'll say X Duke is 69, which is greater than or equal to 10. N minus X Duke and Duke minus X Duke is 36, which is greater than or equal to 10. I have X for the US. Remember, X is the number of successes. 454, which is greater than or equal to 10. And N US minus X US is the failures, which we have there, 226, greater than or equal to 10. So all these conditions are satisfied. So we've checked the conditions for a confidence interval. We want to construct a 95% confidence interval for the difference between the proportions of Duke students and Americans who would be bothered a great deal by the melting of the northern ice cap. I was going to cheat and use this, but let's grab it from your formula sheet. I'm trying to decide. I don't want to run out of time because I don't like that. So I don't want to get caught up here. So from your formula sheet, you want to find your point estimate, P1 hat minus P2 hat. You need your Z star for a 95% confidence interval. We know how to do that. All right. On your T table, what's the table here? I want a 95% confidence interval, and well, I guess it was the one that was highlighted. I need a Z star, which is 1.96. Okay, I'll use the work that they have here. Z star is 1.96. They did calculate the sample proportions for each of the groups, right? P Duke hat, or yeah, usually that's how you read it, is going to be 69 divided by 105. They've rounded to 3 decimal places, which is enough in this scenario, right? And so we're going to use 0.657. PUS hat is going to be 454 divided by 680, which we find is 0.668. What we're ultimately trying to do is compare these two numbers. They are different. They'll never be the same, right? But there's some wiggle room where they're allowed to be slightly different and still be considered the same, right? Just from sample variations and things like that, okay? And so what we want to know is, are these two proportions significantly different from each other? They're different, but how different? And so we have P hat Duke, 0.657, right? Which means 1 minus that is 0.343. And the N for Duke is 105. Doing the same for the US, I have 0.668 times 1 minus 0.668, which is 0.332, divided by N US, which is 680. If you go through and carefully work out, so I like to solve each of these fractions on their own and then add them together and then take the square root. Right? But make sure that you get the same answer here. So you get 1.96 times 0.0497. This is the margin of error. So we'll still have a margin of error even if we have two groups that we're talking about. Right? So we found a confidence interval negative 0.108 up to 0.086. We need to interpret the interval. Interpret the confidence interval. Because although they did here, you never want to build a confidence interval and not interpret it. Your boss would say, oh, I don't know what you're talking about. Right? And so you need to be able to interpret it. We use the same sentence structure as before, right? We built a 95% confidence interval. So let's start there. We are 95% confident the interval from negative 0.108 to 0.086 captures what? Well, whatever we were asked to build an interval of. Construct a 95% confidence interval for the difference between the proportions of Duke students and Americans who would be bothered a great deal by the melting of the northern ice cap. So I'm going to snag this. And just scratch this. Captures the difference between the proportions of Duke students and Americans who would be bothered a great deal by the melting of the northern ice cap. That's long, but just rewording it as an answer, right? That's not hard. What does that mean, though? It goes from a negative to a positive. So from here, so we're done interpreting the confidence interval. Okay. I'll put a little, I don't know what that's called, kind of a the end squiggle. I should look that up because I use them a lot. Okay. But a follow-up would be from this confidence interval, do you suspect that there's a difference in between the proportions of Duke students and Americans who would be bothered, blah, 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 blah. So what I'm going to do is I'm going to paste this thing again and make up a new-ish question, sort of. Using the interval, or the confidence interval, is there evidence of a significant difference between the proportions of Duke students and Americans who would be bothered a great deal by the melting of the northern ice cap? How do we use a confidence interval, right? Is there evidence is basically a hypothesis test, but it also says using the confidence interval, right? Which is where we started introducing hypothesis testing, and then we kind of let it fall off to the side because we developed p-values and things like that. But we can use a confidence interval instead of the test statistic and the p-value. Because I'm 95% confident that this interval captures the true difference. Right? So what you can do is we need to outline our null hypothesis. So that P Duke minus PUS is equal to 0. Or that they're equal to each other, right? But there's a reason I'm doing the equal to 0. Versus the alternative hypothesis, if there's a difference between them, I haven't specified in which direction. So then I just want to know, is it not equal to 0? In fact, just as a side note, we can only, I'll say properly, use a confidence interval for a two-sided test, right? Because the confidence interval gives me area in both tails, right? So we can only properly use a confidence interval to test a two-sided hypothesis, which is what we have. So it's just a side note to get it off my chest, I guess. There, I've said it. But that's not what we're here for. We found an interval, and this is for the difference between the two, right? So we're 95% confident that P Duke minus PUS is somewhere between these two values. And so if you draw, I find the number line is probably the most helpful, negative 0.108 up to, what is it, 0.086. Because I'm going from a negative to a positive, right, I see that 0 is somewhere in here. Right? I'm 95% confident that 0 is a potential difference between these two. Right? And so what we can say is that since a difference of 0 is inside the interval, we do not have enough evidence to reject H naught. Therefore, right, there is not a significant difference, or there is not evidence of a significant difference. How many times can I butcher this thing? One more time. Therefore, there is not evidence of a significant difference between the proportions of Duke students and Americans who would be bothered a great deal by the melting of the northern ice cap. Nice. So you can use confidence intervals to test hypotheses. You still have to state your null and alternative hypothesis, and you still have to state your conclusion, right? And how you phrase your conclusion depends on, well, your confidence interval and whether the hypothesized value is in that interval or not. And then your conclusion in terms of H naught. I'm only expecting you to use the p-value approach on the test. Okay? But I usually like to throw, so I make you do a confidence interval, interpret the confidence interval, and then use that confidence interval to informally test the hypothesis, just like we did here. So that's the confidence interval for a difference in two proportions. Yeah. No, the orange you can kind of ignore. Yeah. Yeah, because the difference between the proportions of Duke and Americans, who would be bothered, is just summarized by P Duke minus P US. What if we had to do a hypothesis? Now, we've already kind of seen it, right, because I snuck it in there. But which of the following is the correct set of hypotheses for testing if the proportion of all Duke students who would be bothered a great deal by the more northern ice cap, I think I skipped a word or two, differs from the proportion of Americans who do? Mostly because we've already seen it. Now, from your formula sheet, you have the general versions of the hypotheses. Either one of these works. I don't have a preference. For me, I choose the one that I like depending on what I'm trying to illustrate, right? And so I used to only use this version because I find that it's more clear, right? P1 equals P2, or it doesn't, right? It's easier to compare the two. Or if you prefer, then technically this is our parameter of interest, right? And how it relates to 0. But we want to know if it differs, which means that first things first, my alternative hypothesis has to have a not equal to in it, right? Which tells me that D is out. Looking at A, P Duke is equal to P US, and P Duke is not equal to P US. I'm happy that that matches this version, right, of your null hypothesis with question-specific subscripts. So that's good. What's the problem with the next one? I pre-selected the red pen. I don't want to hypothesize about the samples, right? P hat Duke and P hat US, I know what those numbers are, and I know they're not the same, right? So that's not of interest to me. We're using those numbers to learn about the population, right? And so here, right, and I will clarify here, we know P hat Duke is not the same as P hat US, right? We can find those numbers since we know everything about each sample. Since we know everything about the samples. The next one looks pretty good. P Duke minus P US is equal to 0. It's just the other version. Let's see if I can pick a color. And take my arrow through here. So both of those are okay. So it just depends. And no, you don't have to do both. You only have to do one of those, right? But be flexible. If I've written it one way and you prefer the other way, that's okay. Right? That's just the answer. For our conditions, for a hypothesis test, kind of leading into it. When we were making a confidence interval for one population proportion, and so I'll emphasize here, right, just one proportion, it's kind of a flashback to one proportion. So for one population proportion, so one sample proportion, then we check if the observed number of successes and failures are at least 10. Right? And how we did that, we had NP hat is greater than or equal to 10, and NQ hat, it has to be greater than or equal to 10. When we were doing a hypothesis test for one population proportion, so for one sample proportion, then we check if the expected number of successes and failures are at least 10, right? Where H naught was that P is equal to P naught. As I've already introduced, right? And then we use this P naught to check our conditions. Problem, as I've already introduced, but it's nice to see it again. When I have two proportions, right? I don't have a P naught anymore, right? It's nice because figuring out what P naught is not usually that easy, right? And so, okay, just comparing the two, I think is a little bit easier, right? Thinking about. But what do I need? I need to find the expected number of successes and the expected number of failures still. So if we're comparing two proportions, where P1 is equal to P2 is your null hypothesis, then there isn't a given null value that we can use, right? And the null value in this case would be P naught, right? There isn't one that we can use to calculate the expected number of successes and failures in each sample. And so what we need to do, therefore, we need to first find a common, which we call pooled proportion for the two groups. And then we use that in our analysis. Like I said, on your formula sheet, right, in the standard error for the hypothesis test, we use that pooled proportion, right? So just as before, right, we use whatever proportion to check our conditions as the standard error in our calculations. So this means finding the proportion of total successes over the total number of observations. Right? And so on your formula sheet, it looks just slightly different. It's like this. I'll bring it in. So they have the number of successes in group 1 plus the number of successes in group 2 divided by N1 plus N2, or some version of that on your formula sheet. Right? Just depends on what information you have. So if we want to calculate the pooled proportion of Duke students and Americans who would be bothered a great deal by the melting of the northern ice cap, let's do that first. Now I have XD and I have XUS, and I have ND and I have NUS. Since I have that information, it's really nice to use the last version on your formula sheet. How small can I make this? Maybe I can sneak it in here. Right, on your formula sheet, if you have the X's and the N's, right, you can just add them up and find a fraction. All right, and so we could find P hat, the pooled proportion, is going to be 69 plus 454 divided by 105 plus 680, which of course they found and rounded to be 0.666. One thing that you'll find is that the pooled proportion, if you've calculated it correctly, should be between the two proportions. Okay? And that's just because you've just done a mashup of the two groups. Right? And so notice that this will go kind of between these two, and that's just a nice way of checking to make sure you've got the right pooled proportion. Okay? Which sample proportion, P hat Duke or P hat US, is the, I can't read this, which sample proportion the pooled estimate is closer to? Is the pooled estimate closer to, and why? It'll be pulled towards the larger group, right? So that's what we see. 0.666 is closer to 0.668 than 0.657, but we also see that it falls between the two values. Right? Nice. So that's a good chunk of work done. I can't remember. I'm just going to, okay, phew. Then we can do this properly. Beep. So I want to do this one by hand. I'll say, see next page. Of course, she's got the shorthand there, but we're going to do it all the way through. Oh. Recall. No, not recall. I'll bring it in when we need it. I was thinking the pooled proportion. So do these data suggest that the proportion of all Duke students who would be bothered a great deal by the melting of the northern ice cap differs from the proportion of all Americans who do? And we're going to do everything to answer this question, so I'm not going to specify that. But do these data suggest means I have to do a hypothesis test. The other clue will be that it's out of 7 marks. Right? So that's a good clue as well. From our confidence interval, we already kind of know the answer, right? But let's see if our full formal hypothesis test supports that. Now, step 0 is to check the conditions or the assumptions. Sometimes we have to just state the assumptions. Now I've got 2 groups, right? And so, and we've already established some notation, right? Using the subscripts Duke and US. And so we're kind of comfortable with a lot of this data set already. And to check the independence condition, I'm going to say for the random aspect, I'm going to say we assume both samples were randomly selected. We assume both samples were randomly selected. the n less than 10% condition, which is optional, but I'll just do it for completeness. And Duke, and we've already seen these conditions checked, which is 105 is less than 10% of all Duke students. Oops. And NUS, which is 680, is also less than 10% of all US, if I can be brief about it. Right, all Americans. That's the independence condition. This is the independence within the groups. I also need to check the independence between the groups. There's nothing really I can do except say, I assume these two groups are independent of each other. Okay? If there's any reason where they wouldn't be independent of each other, right, then you can't use this method. Okay? You'd have to find another test, which exists, but not in this course. Okay? So for us, we need to check independence between as well, right, for two groups. We assume, and I'll be generic, the two groups are independent of each other, right? Of course, you can be more specific, but this isn't what we're here for. So we assume the two groups are independent of each other. Now we're doing a hypothesis test and only a hypothesis test, right? And we already checked the conditions for a confidence interval, and so I'm going to ignore that, and we'll only do a hypothesis test. And so the normality condition for a hypothesis test, specifically, is I need at least 10 expected successes and at least 10 expected failures in each group. Yeah? And so I need at least 10 expected successes in each group. And similarly, copy, paste, I need at least 10 expected failures in each group. The expectation relies on the pooled proportion. So use the pooled proportion. P hat, which we found earlier, was 0.6666. I'll say recall P hat is 0.6666 because we already did that work. Huh? If you haven't done that work, then this is where you would need to do it in order to proceed. Okay. Now, N Duke, oops, times P hat is 105, I want to say. 105 times 0.666, which is, I would expect 105 times 0.666, 69.93, which is greater than 10. Great. And I need NUS times P hat, which is 680 times 0.6666. or 5288 or 0.88, which is also greater than or equal to 10. And I will highlight that this p hat is what I'm using here, here. The failures comes from my q hat, which is 1 minus p hat, which is 1 minus 0.666, which is 0.334. So then I have n duke times q hat, which is 105 times 0.334. Or if you prefer, you could do 105 minus 69.93. Doesn't matter to me. You'll find the same thing. 35.07 is greater than or equal to 10. And then finally, NUS times Q hat is 680 times 0.334. Which is 227.12, which is greater than or equal to 10. Therefore, the conditions for inference are satisfied. Which means we can finally get cracking on our hypothesis test. The actual hypothesis test. Oops. No. I don't know. Step 1. State the hypotheses. On your formula sheet, you have your hypotheses, your two options, remembering to write question-specific subscripts. I like to use the first one. The null hypothesis is that P duke is equal to PUS, or if you prefer, P duke minus PUS is equal to 0. You only need to do one of these. Pick one of these. You don't have to do both. That's crazy. I'm doing both because I want to show you both. Now, we know enough about, oops, I need my pointer. We know enough about the null hypothesis that whatever I talk about here and whatever I talk about here on either side of the equal sign, and still the null hypothesis has an equal sign in it, as always, okay? And so even if you're unsure, your alternative hypothesis must be about how P duke relates to PUS, which means I need to go and read the question and figure out what the sign is for my alternative hypothesis. Pretty sure it was not equal to, but it was a long time ago. Differs. Okay, so are they different? Which tells me that it's a not equal to. I don't care which direction it goes in. And I also like to make a note that this would be a two-sided test. Right? And so here, two-sided test. That's optional. Or if you prefer the other way, you still have to talk about how P duke minus PUS relates to 0. And if they're different, or if they differ, then they would be not equal to 0. Yeah. Step 2. Do the test. Do the do. Doing the test is just shorthand for calculate the test statistic, which is boring to say, I think. But that's going to be your Z calculation from your formula sheet. I prefer the first one. So I'm going to just ignore the second option. If you prefer the second option, that's cool, use it. But you don't have to do both again, right? So I prefer the first version. As long as you're comfortable with what's happened in the second one, right? It's just been, the p hat q hat has been distributed. And I want to recall p hat duke was, oops, sorry, 0. I want to say 857, but I'm not. Way off, 0.657 and 0.668. Way off. And p hat US was 0.668, and also p hat, the pooled proportion, was 0.666. I also have N1 and N2, which using question specific subscripts would be N duke and N US. Now, I know I've been harping about the question specific subscripts, but in the formula, it's way too annoying to write with question specific subscripts. And so I'm going to say something like, let this be group 1 and let this be group 2. As long as you define it, it's okay. I'll really only be looking for the question specific subscripts in your hypotheses, right? Because that's where you want to be really clear, especially if you're claiming one's less than the other one. So N duke is 105 and N US is 680. And then we have all the information that we need to fill in our Z. So our Z is 0.657 minus 0.668. How far is that from 0 technically? Divided by the square root of 0.666 times 0.334, 1 minus 0.666, times 1 over 105 plus 1 over 680. It's a lot of math. Still only worth 1 mark, right? Which takes some pressure off, right? If you're not comfortable doing this on your calculator, then give me a reasonable value for Z, right? What's a reasonable value? Between -3 and +3 usually. Okay, 0.657 minus 0.668. You can feel it breathing down my neck. -0.011. And I'm just going to go for it. 1 divided by 105 plus bracket 1 divided by 680 times 0.666 times 0.334, square root that, divided by 0.04945339033, negative 0.011 divided by that, get a Z of negative 0.222431666. That means that this difference is only 0.22 standard errors away from zero, right below zero. Not very far at all. And so now for our step 3 is find the p-value. I like to set it up and then fill in the blanks once I have my table in front of me. And so usually what I do is I write using the t-table. Just nice to show that you know where to go for this thing. We find the absolute value of z equal to negative 0.222. Remember, we need at least 3 decimal places just to match the table. And it's going to be between 2 values, which I'm holding off on looking at the table until I have it, but I have a pretty good idea. And from there, I'm going to find the two-sided p-value. Now, with my little itty-bitty time left, I'm going to copy this. And put it here. Do you remember what we said? There are end caps on here, right? And so here we could start at 0. And the one-sided p-value at 0 is 0.5. And the two-sided p-value at 0 would be 1. Right? The area in both the tails from 0. Because then when I take my absolute value, I drop the negative. 0.222 is going to be between these two values. And I want a two-sided p-value. So it's going to look like this. My z is somewhere between 0 and 0.674. And my two-sided p-value, making sure you list them from smallest to largest, is going to be somewhere between 0.50 and 1. That's huge. It's not less than 0.05, which is what it needs to be in order to reject H0, right? And so with my few precious moments here, I'm going to write my conclusion. Step 4, the conclusion. Show off what your p-value is and how it compares to the alpha level. I'll do it quickly here. Since the two-sided p-value is between 0.50 and 1, it is not less than the assumed alpha level of 0.05. That's the first part of the conclusion, which means we do not have enough evidence to reject H0, period. Therefore, and that matches what we found with our confidence interval, as it should, right? And so therefore, and I'm just going to snag the question, copy it. Copy. Paste. Therefore, these data do not suggests that the proportion of all Duke students who would be bothered a great deal by the melting of the northern ice cap differs from the proportion of all Americans who do, period. And with that, I release you. Great job. Enjoy your Halloween. See you next week. See you.